Welcome, everybody. This is lesson number one in light and geometric optics. Today we are going to be looking at light energy in a wave. We're going to be looking at the different components of light and what the waves actually look like, and then measuring some parameters or some quantities within those waves. So, if we're talking about light, you have to understand that light does act like a wave, and it is able to transfer energy from one point to another without transferring any matter or material. And that's why light is able to travel through the vacuum of space. There's no particles in between, but it's able to do that. So when we talk about a wave, and we're talking about waves of light, what we're talking about is this disturbance that transfers energy from one point to another without having to transfer any matter there. You are already familiar with lots of different types of light. So, for example, you're familiar with visible light as you are looking at a screen right now. And so you are familiar with that because you are able to sense that you're able to see that. There's other types of light that you are not able to see with your eyes, and that includes different types of electromagnetic radiation that you can sense in other ways. So, for example, radio waves, we use radio waves to communicate. So you guys probably have listen to Z103 or something like that over the radio. All of that information that's being transferred from the radio station to ultimately your radio is a type of electromagnetic radiation. It's a type of light. It's just we can't see it. There's other types of light that you also can't see, things like infrared radiation, but you can experience those things. If you've ever sat in front of a bonfire or a fireplace inside your home, you are experiencing, you're sensing that light there. Now, of course, we can't see that light, but you do feel its effects. So when we look at light as a wave, we have to look at how that wave is actually put together. And there's some parameters, some components of those waves that we need to talk about in order to understand what it is that we are measuring here. So the first thing that we're going to look at is called the wavelength. It is denoted by this symbol here. That's the Greek lowercase l. I'll draw one out for you because it shows a little bit different via text. The Greek letter L is drawn kind of like this. Okay, and that L is called a lambda, and that represents wavelength. When we're talking about wavelength, we're talking about the distance from one place to the next similar place on a particular wave. So, for example, let's say we were talking about this location here. You'll notice that's at the crest, the top of the wave. If we look at the second crest, which is over here, and we measure the distance between crest to crest, that's what we call one wavelength. And those are measured in meters or centimeters. And that's just one feature of these waves. Now, each type or each different type of electromagnetic radiation or light has different wavelengths, and then of course different features as well. We don't necessarily have to measure from crest to crest. We can also measure from trough to trough as another example. This also represents one wavelength. So in any case, all you need to do is just measure the distance between the same spots at the top or at the bottom of different waves, and you'll be able to determine what its actual wavelength is. Another feature of a wave is called the amplitude. So the amplitude is the wave height from its resting position. Now in the second diagram here, you can't really see the resting position, but you would imagine that somewhere in the middle of this line here, or this wave, there is the resting position where it's at that 0 point. And when we're talking about amplitude, we're talking about from that point to the top of the wave. That's what we would call amplitude. Or if we're measuring from that rest position, we can also measure downwards, and that is the bottom of the crest, but it's also representing the amplitude, so from the rest position upwards. And of course, if we alternate that, you get different amplitudes. That's what our radio stations use. Some radio stations, I should say, use to give us the different stations. So AM radio, for example, AM stands for amplitude modulated. So what each radio station does is they change the height of the wave that you are listening to. And then the next part, which is actually down here, is frequency. So you guys are probably most familiar with FM radio, and that is frequency modulated. And we'll talk about what that means in just a second. So frequency looks at the rate of repetition of the waves. In other words, how quickly are these waves passing by a particular point in space? So for example, if I had to draw something out here, let's say this was my particular point in space, this line that I've drawn here, and I start drawing a wave, and this wave, let's say, is moving in this direction, so maybe from the radio station to your radio. We want to know how many times every single second does one of these wavelengths, so maybe from crest to crest here, how many times each second do these things pass by this particular point in space? And that's what we're talking about, frequency. And we're looking at the number of cycles or the number of wavelengths, for example, per second that pass by a particular point in space. And that's what we call the frequency. And so, of course, when we look at FM radio, frequency modulated stations or FM stations, they change how quickly or how many cycles pass by every second past a particular point in space. And that's how they do that. So AM stations, they're all on the same frequency, they just alternate amplitude, whereas FM stations, they'll all alternate frequency. Now, when we're talking about frequency, there's specific units for frequency, and we call them hertz. You guys can see that right. Oops, pen's not working. You guys can see that right here. These are hertz, and they're denoted by a capital H lowercase z, and they represent, as I mentioned already, the number of cycles per second. When we look at hertz and we compare it to wavelength, the frequency, and we compare it to the wavelength, you have to remember that there is a relationship between frequency and the wavelength. Of course, the longer the wave that you have, the more wave has to pass that particular point. Remember, we were talking about that particular point over here, over the same period of time. Now remember, these things are all moving at the speed of light. And so if I make a longer wave, I'm going to have fewer of these cycles passing every single second. If I have a shorter wave, more of these cycles will pass per second. And so you start to develop or see that there's a relationship between frequency and wavelength. As the frequency increases, you must decrease the wavelength, because remember, they're all moving at the same speed. But what happens is that as we move across, if we've got a higher frequency, we must have a shorter wavelength because we've got to get more cycles in per second. The opposite is also true. If frequency is decreasing, that means wavelength is going to be increasing. Now, we have some equations here that are useful to us. And so we can actually look at some of the features of the electromagnetic spectrum and their measured quantities. And we're able to do some calculations to give us some information about the actual waves themselves. So we know that the velocity, that is the distance over time that these waves possess, is equal to the frequency times the wavelength. We also have another relationship, which is shown up here with these red arrows, in that frequency is 1 over that period in seconds. Okay, so there's an inversely proportional relationship between these two. So we've got some different variables here. We've got v for speed, which is our distance over time. F here is our frequency, which represents hertz. Now, hertz also has SI units that are attached to it, and those SI units are 1 over S, or how many per second, and sometimes it's denoted with S to the minus 1. Of course, wavelength is a distance. It's measured in meters or in centimeters. And then lastly is our period in seconds, our time period there. So it says here, I've got two sample problems here. It says if the wavelength of a wave is 10 centimeters and its frequency is 5 cycles per second, or 5 hertz, what is its speed? And so if we take a look, we have an equation here. Speed is our letter V here. So V is equal to F multiplied by lambda. And so if I write down all the information I know, I'm looking for V, so that one's a question mark there. But I do know the frequency here, and the frequency in this particular question is 5 per second, or seconds to the minus 1. And I also know that my lambda here has a wavelength of 10 centimeters. And so I can actually take these two bits of information and start plugging them into the equation. Now, the nice part about these equations is that no matter what we do, our units are always going to cancel out to produce the units that we want to ultimately get to. So if we look at speed, it's a distance over time, meters per second, centimeters per second, or whatever it might be. So let's try and work this first problem out here and see what happens. So if I know that v is equal to f times lambda, and I know that my frequency is 5, pardon me, the pen is a little wonky, 5, one over s, that's the units, seconds to the minus 1. Remember, I showed you that up here. It's the same thing. Multiplied by our lambda, which is 10 centimeters. Notice that the units are completely different from both of these things. And so what ends up happening is the units just carry across. Centimeters is multiplied by 1, and seconds is multiplied by 1 in the denominator and the other one. So we have 5 times 10, which produces 50 centimeters per second here. And that is the speed at which these cycles are passing by. So very interesting. The second problem I have here is a wavelength problem again. It's asking what the wavelength of a wave is if its speed is 200 centimeters per second and its frequency is 15 hertz. So let's go through and actually figure this out. So we know that the equation is v is equal to f multiplied by lambda. We aren't interested in this equation. We need to rearrange this equation to produce an equation that says lambda equals. So what's going on between f and lambda is a multiplication. So in order to rearrange this equation, we would move the f to the denominator on the other side of the expression here. And so you end up with an equation that looks like this. And let's see if I can get the pen to work. There we go. So v Okay guys, I finally got the pen to start working again. So if we look here, we're being asked to calculate out what the wavelength of light is. So we're going to be looking for something that ends in either centimeters or meters for length here. So when we're looking at this equation, we know that we are given the speed, which is 200 centimeters per second, and we're given the frequency in 15 hertz. So when we look at this equation, we want to get this lambda here, but we need to rearrange the equation to give us an equation that says lambda equals. And so if I look at what's happening between frequency and lambda, there's a multiplication there. So in order to get rid of that, I have to reverse that multiplication. So we have to remove the frequency to the other side of the equation. So we've got v over f is equal to lambda. So when I start plugging in my information, I know my v value, which is 200 centimeters per second. So I'll write that on there, 200 centimeters per second. And I know that my frequency has units of 15 hertz, but you'll remember from up above that I don't necessarily have to use hertz as the units. I can use 1 over s, or seconds to the minus 1. And so I can put that in here, 15 seconds to the minus 1 here. And that, of course, is going to be equal to lambda. When I plug in these values into a calculator, I end up with a value of 13.333 continued. Now, of course, there's units attached to this. Now, we got to check out what those units are. We're going to have to cancel out the units. So if we take a look here, this seconds in the numerator that you guys see here is actually in the denominator position because it's centimeters over seconds. And you'll notice that this centimeters, which is, or this seconds, which is in the denominator, has a -1 exponent to it, which flips where its actual position is. So instead of being in the denominator, this one's in the numerator. If I have seconds in the numerator and seconds in the denominator, they end up canceling out. And so the only units that I have here are centimeters. So those remain as the units that we are interested in. And ultimately what that means is we have the correct units. We are looking for a wavelength. Wavelengths are measured in either meters or centimeters.